All right. So let's do that. Perfect. Can everyone see my iPad screen? I don't know how to hear you. Can you guys hear my iPad screen? Is that or see my iPad screen, I guess. Is that working? Beauty. Okay. So the reality is, we are just a few days behind because of yesterday. Um, and today I'm going to briefly go over some of the lessons. We won't cover absolutely everything in detail, but I'll go over these concepts so you at least have an idea and so you can start looking at some of those future questions. I see Cam already submitted his entire assignment, so that's impressive. I did also bump back the due dates of the assignment. So I bumped it to the Friday and I bumped the exam to the Monday. So when we reconvene on Thursday, because you don't have school tomorrow, we'll discuss those dates and discuss whether or not those are the finalized dates. And then as we keep moving, I'll have to kind of reschedule and kind of figure out what's going on. Last time we were together, we looked at formal charges. We looked at Lewis structures. And today we're going to look at the formal charges of those structures. Um, so any Lewis structure needs a formal charge to be assigned to it, and that will give us a clue whether or not our Lewis structure is actually correct. So when we were drawing diagrams on whatever day we were at school on the Friday, I had given you one example and said, "This is correct. This is the final version." Um, but what I didn't explain to you is that there are actually multiple correct versions that you can assign. So on the left hand side over here, you can see CO2. There's two different versions. There's five different versions, excuse me, of CO2 and what it can look like. And so what we want to do when we're choosing the correct Lewis structure is we want to choose the one that has the lowest charges. So A, B, C, D, and E are all correct. But in terms of when I'm marking you an exam or whenever you're drawing a Lewis structure, you want the most stable structure, and the most stable structure will have the least charge possible. So you can see on this top one here, we have zeros as far as the carbon, the oxygen, and the other oxygen. They all have zeros as their charge. I'll explain how to calculate that. But that would tell us then that that one must be the most stable. The one, if we just focus in on E over here, one of the oxygens is -1. I guess the other oxygen is a +2, and the other one's a -1. So technically, the overall charge of that, the overall charge is 0. You have two negative ones and a +2. So the overall charge is 0. However, because everything has a charge, it's not going to be very stable. So, in terms of how you calculate formal charge, you're going to use this formula, which is valence electrons minus sticks minus dots. And so, when we're looking at the example down below here, if we look specifically at carbon in blue, you can see that there's one, two, three, four bonds around it. And you would then go to the periodic table, say, okay, I know carbon has a valence number of 4, and then you would be able to determine that 4 minus 4 is 0. In terms of hydrogen, you would find that its valence number is 1. It only has one bond happening here, and that's in between the carbon and the hydrogen, and so 1 minus 1 is 0. Oxygen gets a little bit more confusing. You have 4 dots, you have 2 bonds, and you know the valence, the number of valence electrons oxygen has is 6. And so 6 minus 2 minus 4 is equal to 0. Now, the other thing that we can check is I talked about the octet rule. I talked about the octet rule on Friday. This oxygen here still satisfies that octet rule where you have 4 valence electrons and then you also have 2 bonds. And we said that each bond counted as 2 electrons. For the purpose of formal charge, we do not count the bonds as 2 electrons. We just say they're a bond. Or in the equation, we say that they are a stick. As far as indicating formal charge goes, I prefer this. I prefer this method here, where once you finally have your finalized structure, you put square brackets around the entire thing, and then in the top right corner indicate what the charge of that thing is. So in this case, we're looking at NO3, and you've worked with NO3 quite a few times. If you have your table of ions, you'd know that that's just nitrate. And in grade 10, you would have seen, okay, NO3 is just simply nitrate. Easy. It's got a -1 charge. I can swap and drop that. Now we're drawing it out and explaining why NO3 has a -1 charge. So if we look at the structure over on the left here, we can see that oxygen, normally a valence number of 6, it's got 2 bonds and it's got 4 valence electrons. So that one's going to be equal to 0 in terms of its charge. The ones on the bottom, however, again, 6 is the valence number. They have 6 dots and 1 bond. So they're actually going to be equal to a -1. Both of them will be. And then looking at nitrogen, nitrogen has a valence number, or we know that it has 5 valence electrons. But in this case, it just has 4 bonds. And so we know that this will be a +1. To calculate the overall charge, you just add up all of the charges of the individual atoms. So we have a 0, +1, -1, and -1. Add those together, you end up getting a -1 total charge, or as it's shown up in the top right corner here, that negative charge up here. Okay. So there's a few examples that we're going to try. So I'm going to draw these out, and then I'll erase everything, and I'll draw the next one out, and then I'll erase everything. So we have H2O. If this one, I said that the oxygen would probably be the central atom. We said hydrogens are always going to be the terminal atoms. So I know that we have a situation like this. I also intentionally did not do these this morning so that you can see the process of me figuring out where the bonds all need to go. Now, I've drawn water out way too many times, so I know that hydrogen has 1 valence electron and oxygen has 6. And so as far as connecting the dots go, it's really easy to just connect these like that. And I know that that would be H2O. And then I would calculate um, the overall formal charge. Hydrogen has a valence number of 1. It only has 1 bond, so we know that that's 0. This other hydrogen, same thing. And then we can check oxygen here, where we have 4 dots, 2 lines. And so we know that this entire charge of this thing would be 0. And you will know what the final answer should be based on whether or not there's a charge in the top corner of any of these atoms. So I think for that 42 mark question, I gave you some that have charges and some that do not. You will know that you need to do this calculation and have it equal whatever the charge is. Are there any questions so far? It's my least favorite Zoom question. Go ahead if you have a question. Perfect. I love talking to myself. It's my favorite thing to do. All right, next one, CO3 -2. Now, when I'm drawing that one, I know that oxygen can be a central atom. I know that carbon is always a central atom, so I'd put it in the middle. My other clue for this one would be I only have 1 carbon, but 3 oxygens. So it would make more sense that you put the one solo thing in the middle. So I'm going to put my 1 carbon here, 1, 2, 3 oxygens surrounding it like that. Let's make this a little bit neater. Let's do it like this. 1, 2, 3 oxygens like that. Carbon I know has 1, 2, 3, 4. Oxygen has 6. Like that. So right away I can see the potential that those two are going to bond up like that. And those other two are going to bond up like that, where we'll have single bonds. I see that I have one more lone electron on carbon. And so what I'm going to do is shuffle these oxygen ones around. Put that other lone one here. Ooh, hello, that was exciting. Sorry. and I'm going to form a double bond like this. So now what I have is I have these two weird lone electrons floating by themselves. There's nothing I can do with these right now. There's nothing left on carbon for them to bond with, and it doesn't make any sense for these two oxygens to bond together. Um, Partially, that's because it would form a very unstable shape. Um, yeah, you wouldn't see those oxygens end up bonding together. Mostly because they're terminal atoms, they want to be on the outside and they want to be as far away from each other as they can. And if they bond, they're prevented from doing so. Um, and so what we would then do is we would look at this example and we calculate all the formal charges. So carbon here, I know it has a valence number of 4, and I know it has 4 bonds attached to it, so it's got a 0. Oxygen here has a valence number of 6, 4 dots, 2 lines. That oxygen's a 0. Looking at this other oxygen, we can see, well, it's got a valence number of 6, but it has right now, it has 1, 2, 3, 4, 5 dots and 1 bond like that. So that one, I guess, in theory is 0. And then down below, we would have the exact same situation. -5 minus 1 is equal to 0. And so looking at this, I'd look at this particular structure and I'd say, well, this must not have worked. And the reason that I know that this must not have worked is I see that I have the wrong number of valence charges over on these two sides. So I see that for my oxygen and my other oxygen, everything here is adding up to 0. I wanted this to add up to -2 instead. That's what I ideally wanted this to add up to. And so I would look at this structure here then, um, and I want to eventually generate a -2 charge. And so I know that there either must be another electron from the oxygen, um, or I know that they're going to form a double bond of some sort. And the actual structure of CO3, oh my word, how does it do that? Oops, sorry, I'm flipping around. The actual structure of CO3 ends up being like this. So it has a couple different forms that it can take. So what we can consider when looking at this one is 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, is we would add up the number of valence electrons. So oxygen has 6 plus 6 plus 6, and carbon has 4. So 6 is 18. We should have 22 dots drawn somewhere on this page. And so if I'm looking at this example here, I can see that I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22 different dots drawn. So what I know then is I know that this thing must have gained 2 electrons from somewhere. And so that's the valence electron method that we were talking about the other day, where we were saying, well, if it has a -2 charge, does that mean it gained or lost electrons? We know that this thing must have gained 2 additional electrons, meaning this number must be 24 instead. So where that comes into play is right now these two oxygens are breaking the octet rule. And so those two other electrons, this one here and this one here, would get added on by it reacting with something. And that's where that -2 charge is coming in, is that it's gaining those 2 additional electrons. Questions about CO3 minus 2? The reason that there's 3 different structures shown here is just to show you that These are called resonance forms or resonance structures. And those basically say like any one of these three is possible. Any one of those three is possible. Um, and they're all equally correct. It just depends on how you turn the molecule visually and actually look at it. So if we were to redo these calculations, we would then say that this would be 6 minus 1. And that would change these final answers then to a -1 and to a -1. And so you'd show that like this. You'd draw little -1s beside it and put a little circle around it. Okay, so that's CO3 minus 2. Next example is SO2. Again, I'm guessing S will be in the middle of this one. I also know that sulfur is in the same column as oxygen. So I know that sulfur is going to have 1, 2, 3, 4, 5, 6 different valence electrons. Um, and I know that oxygen will also have 1, 2, 3, 4, 6 valence electrons. Now I'm going to show this one to you early, just so you can see kind of what we're looking for. So our eventual goal is we want to create the one on the left here. We want to create that SO2 on the left. And the way that we can actually go about doing that, so I'm just confirming with my periodic table that sulfur has 6 valence electrons. It should. Yes, it has 6. So what we can start doing then with this is we see these two bonds, super easy to form those two. 1, 2, like such. We then have this awkward scenario where we have this singular electron out here and this singular electron out here. Now, what we can do with this is we say, okay, I have 4 electrons left on sulfur. If I take 2 of them and form bonds with the oxygen, so if I take one from each side of this sulfur and form bonds with the oxygen, that'll still technically be stable. Because right now what we have is we have a 6 valence electrons, 5 minus 1 is equal to 0. 6 valence electrons, 5 minus 1 is equal to 0. And then on sulfur, we have 6 minus 6, which is also equal to 0. So technically, this is balanced. However, the situation that we're left with here is that we have those 2 singular electrons on the outside of our structure. Quinn, how I'm getting those numbers is I'm saying I know oxygen has 6 valence electrons. It has 5 dots around it, and it has 1 bond. So that's where I'm getting those numbers from. So the problem with this structure is because we have those singular electrons on the outside, this structure is not going to be very stable. I said that whenever we can, we want to form pairs or we want to form a buddy system. And so what I'll do here is I'll take both of those singular electrons and they'll form a bond. And I'll do the same thing on the other side. So I broke up a pair of electrons to form 2 different bonds like this. And so if we were to look at our periodic table, oxygen has a valence number of 6. And then we have oxygen here, which has 4 dots and 2 bonds. And so we know that this one will be 0. Sid, are you asking about the sulfur, where it was like 6 minus 4 minus 2 like this? Did I write minus 1? Okay, so that was a super mistake then. I was trying to think of like the next 7 words I would say, and that was a mistake that I made. Yeah. So in each one of these, we have 6 minus 4 minus 2, and we have all zeros. So the reason that this structure takes priority over the other one that we had is because the other one had two singular electrons, and we do not like those singular electrons. They're lonely, and we don't want electrons to ever be lonely. And so this would be the final structure we'd end up getting. Any other questions about this one? This one's a weird one. Again, sulfur is one of our exceptions, so we'll talk about that one. But if you were to look at just simply the octet rule here, it breaks it. This one technically right now has 10 electrons surrounding it, and that is fine because sulfur, as we'll talk about in the next PowerPoint, is one of those ones that breaks the rules. Okay, if there's no other questions, I'm going to just erase this. Awesome. Next example is ClO3 with a -1 charge. For this particular one, this one's a weird one. Um, Typically, we'd expect to find chloride on the outside as a terminal atom instead of a central atom. In this particular case, we're going to use it as a central atom. How I know that we're going to do that is that I have three oxygens and only one chlorine. So again, same with the CO3 where we put carbon in the middle. Usually what you have like one thing of, that will end up going in the middle. So we're going to try doing this. Cl, O, O, and O. And we know that we would prefer this, and we must have eventually a -1 charge on this. I shouldn't have drawn these yet. My bad. So what I'm going to do here is I'm going to just draw. Stop. I'm going to draw these 4 electrons, and then I'm going to draw these 2 single electrons. And I'm doing this so that these single electrons are a little bit easier to move around, because I'm guessing I'll need to make bonds with them. So chlorine has 1, 2, 3, 4, 5, 6, 7 valence electrons. It's in the 7th column of the periodic table, so it has 7 valence electrons. This is another one of those weird ones where I'm going to actually draw it differently. Instead of drawing them as pairs of electrons, just so I can visually see the difference 1, 2, 3, 4, 5, 6, 7, like this. I'm just going to draw them surrounding so I can see what potential combinations there are. Drawing them with the pairs is technically the correct way. So drawing them like this is the correct way. But in order to make a stable structure, we're going to break up these pairs of electrons since we have so many singular electrons surrounding this chloride. So this one, that combination's easy. And for some of you, you might get to this point and be like, I don't really know where to go from here. What we're going to do is just slowly start picking off one by one the electrons of chlorine until we're left with either a lone pair or no electrons surrounding it. Double bond like that. This single bond here like this. And now the thing that I have left here is I also have the knowledge that this thing has a -1 charge. And so I've sort of been saving this for last, but I have one additional electron that I can add anywhere that I want. And so for me, what I'm going to do is I'm going to add this electron here on the oxygen. So the big one, I'm just showing you it larger. So I'm showing you where that electron was added in. And I know that that came from the -1 charge, that this particular molecule had one additional electron that I could add wherever I wanted it to. So if we're to check the formal charges of this, I would look at oxygen here and see that this has a formal or a valence number of 6. There's 4 dots and 2 lines, so it's 0. Same thing with the bottom. If I look at chlorine here, I have a valence number of 7. I have 5 bonds on it and 2 electrons on it. So I know that that one's also 0. And then if I look at the oxygen valence number of 6, there are 6 dots, 1 line, so I know that this will be a -1. And if we get that -1, then we know that we've drawn it correctly. We have zeros everywhere except on that oxygen. So we know we've drawn that correctly. And if I scroll down just a little bit, there's our correct answer. Again, I said it does not matter which side the single bonded or negatively charged oxygen goes on. It doesn't matter which side it's on, so long as it's there. So some kind of key notes for you are if it has a negative charge, add one more electron later. If it has a positive charge, you'd obviously do the reverse of that and take away one electron. And then you can confirm your structure with the formal charge and no lone electrons. Questions about that one? If negative, add one more electron later. Yeah, cool. Lana, is as far as how you know where to add the electron. So for us, what we were looking at before I added that electron was this. So for me, it doesn't make any sense to add the electron here because then it just creates another singular or lone electron. That's useless to me. It also doesn't make sense for me to add it here. I could make a double bond here, like this, um, by connecting with this electron. But what that does then is that actually messes with. That was a lot of noises from somewhere. That messes with the formal charges. So if we did it this way, the chlorine would instead be 7 minus 1, 2, 3, 4, 5, 6, 7, 8. It'd be like that. And then the oxygen, I guess technically the oxygen would be 0. So this is technically also the correct answer. Yeah, because this oxygen would also be equal to 0. So that is technically also a correct answer that you could have. Um, but what that does is it really messes with chlorine in terms of the octet rule. So if I instead put my lone electron here, I still had the lone electron on oxygen. I connected those 2 dots. Stop doing that. And ended up with this. What this does is now chlorine has 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Chlorine has 14 electrons surrounding it. That is a hard no bueno. Chlorine does not want that many electrons. This one does still technically break the octet rule, but less. So now there's only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's only 12 electrons around chlorine instead. How do you know when to stop making double bonds? Is that what you're wondering? So you base that off of the octet rule. So normally, without exceptions, now this one's a bad example because it is an exception. You would look at each of these atoms and say, okay, let's look at oxygen over here. It has 2 or 4 valence electrons surrounding it, or 2 lone pairs. And there's also 2 bonds. And so what that means is that there's 8 electrons surrounding it. Same is true about this oxygen here. There's 8 electrons surrounding it. Same is true about this one. There's 8 electrons surrounding it. Now, as I said, chlorine's a bad example because it's an exception to that rule. But generally, you know to stop making bonds once you've reached 8 electrons, whether that be the bonds, which are worth 2 electrons, or the lone pairs over here. Once you've reached 8 electrons around an atom, you stop. That's how you know when to stop doing the the bonding, the double bonds or triple bonds, etc. Yeah. Other questions? We're at the end of the first PowerPoint, the formal charge PowerPoint. Yep. Okay, we're go ahead. I, I'm recording it, so I'll post it to YouTube and then post the link to you guys. Yep. Yep. That's the one. Okay. Let's go to the next example here, which makes a bit more sense than that one. The next PowerPoint we do today is going to be just formal charges and the exceptions to the rules. So CH4, I finished with a really easy one. Good for me. I know that hydrogen has a valence number of 1. I know that carbon has a valence number of 4. This one's super easy. There's no charge on it. It's just simply a fun little game of connect the dots. That one's easy. That one's a fun one. Lewis structures get easier and easier with practice. So the more scenarios and the more interesting cases that you see, the easier they get. Of this page, I think the 2 really hard ones were this one here and this one here. And the big reason was the charges of them. And the other reason was trying to confirm, like, am I doing the octet rule correct? So the 3 suggestions that I would have for your Lewis structures are, if there's a negative charge on something, add that last electron, add it later, add it towards the end. Confirm the structure with the formal charges. You also will confirm the structure. Confirm the structure with the octet rule. So you want 8 surrounding electrons, like such. Other questions, or should we move on to the next PowerPoint? Cool. Let's do the next PowerPoint then. Yeah, you guys already have all of these notes in your notes package if you brought those home. Okay, so as I mentioned, there are exceptions. Chem is awesome because, and I say that very sarcastically, because there are always exceptions that break the rules. And I'm sure that many of you feel that way about chem already, where it's like, this is so dumb. Like, my teacher told me it's always this rule, but then gave me 3 examples where it's not the rule. And that also frustrated me in high school and in university, because I felt like I never knew what that exception was or why I was doing something different. So, my hope is that as your teacher, I can teach you why those exceptions exist, or how to better prepare yourself so that when the exceptions come up on an exam or otherwise, that you're ready and prepared for it. So, the ones that tend to break the rules are electron odd species. So that would be like three valence electrons, or five valence electrons, or seven valence electrons. Um, VAL and then the E with the little negative sign. That's just my short form for writing valence electrons, so I don't write the word out 1,000 times. But anything with three, five, or seven valence electrons is going to create a problem for us, considering that we need to meet the octet rule, which is eight, which is an even number. So somehow with some species that has five or three or seven valence electrons, we need to get to eight. And that's a difficult part of this. Where that particularly comes into play would be an example like NO2. So nitrogen in this case will be the central atom. I know that because there's multiple oxygens. And so if you've been doing chemistry, I guess, for a long period of time, you'll know that most of the time NO2 has a negative charge. It is possible, however, that NO2 does not have a negative charge. There is a potential scenario where that exists and there's not that negative charge. Here's what that one looks like. So nitrogen has one, two, three, four, five electrons like this. Oxygen has six valence electrons like this. So really easy. These two obviously will connect and make a bond. You have a singular electron on nitrogen left over and a singular electron on oxygen left over, so we can use those to, make a bond there as well. And then what we would need to do is just simply count up the number of electrons and see if we can get this to even out. So right now what we have is we have nitrogen, which has a valence number of 5. We have 2 dots and 3 bonds. So that one's 0. So far it's looking promising. Oxygen has a valence number of 6, and we have 4 dots and 2 bonds. So we're looking at a 0 there as well. Things are looking good. So when we come over to the other oxygen here, we have 6. We have 6 valence electrons. Or sorry, 6 is the valence electron number that it has. There's 5 dots and 1 bond. Also 0. Things are looking great. As far as I know, based on formal charge, this is the correct structure. However, there is a problem. I said that there were 2 ways of confirming whether you had the right structure or not. One of them was the formal charge, the other one was the octet rule. Right now, oxygen does not have 8 surrounding electrons. It only has 7. That is a problem. And so what we would typically see with this one then is nitrogen, because it has 5 valence electrons, or because it has an odd number of valence electrons normally, it can break that rule. So what will happen then is, instead of this pair of electrons up here existing, that electron will migrate over onto the side of oxygen. And so now oxygen has 8 surrounding electrons. So the octet rule is good. This oxygen, we didn't touch anything, so it stays the same. The octet rule is also good. But now what we need to do is recalculate these formal charges, because they will not be equal to 0 anymore. The octet rule for nitrogen is broken, but that's fine, because nitrogen is an electron odd species. It has 5 valence electrons normally. So if we break the valence number or break the octet rule, it doesn't matter. Who cares? So looking at oxygen now, we see we have 6 dots, 1 bond. We have a negative 1 charge on that oxygen. Looking at nitrogen, which normally has a valence number of 5, we have 1 dot, 3 bonds, so we have a plus 1 there. So I'm going to write plus 1. Let's do it in white. Plus 1 right here, minus 1. And so because those charges offset, we know that this now doesn't have a charge whatsoever. And so we would say that this must be the final and complete Lewis dot diagram. So again, the weird rule with this one was the first drawing I did, oxygen did not meet the octet rule. It only had 7 surrounding electrons, and that's a problem for oxygen. But for nitrogen, it's no problem. He has no issues breaking the octet rule because he has 5 valence electrons normally. Questions about that one? Where'd I get this? So this is normally what nitrogen looks like, is this. And that's nitrite. So normally it exists as an ion. It can, however, exist without a charge. And so that's what we're drawing down here is we are drawing the uh, covalent compound or molecular compound that does not have a charge. So the beautiful thing about electrons is that they're kind of free to do whatever the heck they want. And what that can result in is that can result in molecules that have charges. It can also result in molecules that do not have charges. Okay. This slide isn't super important, but basically what it's saying is we refer to electron odd species as paramagnetic. Um, in other words, this paramagnetic means that there is a electron. So in this case, this one here, electron that isn't paired up or doesn't make a bond, that would be called paramagnetic. Any other compound that has all bonds or all pairs of electrons is called diamagnetic. So that's what that sentence there says. Other than that, this slide's super not important. Ones that can form incomplete octets. This is usually the 3 valence electrons. And if you look at your periodic table, boron is the only non-metal that has a valence number of 3. And so it's the only one that'll actually end up doing this because it's the only one that can form a molecular compound. It's the only non-metal with a valence number of 3. And so this is basically the only case or the only molecule that you'll see this, and it's boron trifluoride. So boron has a valence number of 3. Fluoride, all of these will have a valence number of 7. So draw 7 dots around those guys. And then as far as making bonds on this one, it's pretty straightforward. It's like that. We would check the formal charge just to see. So fluoride, we said valence number of 7, 6 dots, 1 bond. It's equal to 0. And that'll be true for all of these. Oh, I did. I don't know why it's not showing. I did on my iPad. Ooh, interesting. Come on, Zoom. Don't be the worst. Okay, give me one sec. Okay. Sorry. Let me open this. Um, Sorry, my iPad. um, Sorry, folks. My iPad and the Zoom app did not want to work together. So let's go share screen, start broadcast. That's why you guys stop seeing things. Okay. There it is. Nope. Boron doesn't. Boron only has 6. Right. So when I say surrounded by, you would look at boron and say, okay, this is what boron looks like. It's got 3 bonds around it. In other words, it has 6 electrons around it. So you look individually at each atom. So you would look specific, you'd kind of zoom in on, actually, I can do this technology. You'd zoom in on just fluorine and look at just, oh man, I'm making so many mistakes today. Just fluorine and say, are there 8 electrons there? And you'd say, yes, there are 6 lone pair electrons. And then there's a bond which counts as 2 electrons. So yes, it has 8 around it. Correct. Now boron's an exception because it only actually has. So let's just do this. It only has 6 electrons around it, and that's fine. So that's called an incomplete octet. And the reason being, boron is so small and it normally only has 3 valence electrons that it could not care less if there were 8 electrons around it or not. And again, I said this will be the most common example that you see. I just might replace fluoride with like chloride or iodide, other things that have 7 valence electrons around them. But they'd all look exactly like this. So 7 is the valence number, 6 is the number of dots, 1 is the number of bonds. Here is just another picture of this. Now, I don't love this picture because what it fails to show you is the NH3 would actually have 2 valence electrons or a lone pair on the ammonia, but boron trifluoride, it looks exactly like this. It's completely fine. Last exception. So the 3 that we talk about is incomplete octets, electron odd species. So that's the 3, 5, and 7. And then expanded valence shell. And I told you that this was the kids program PBS. That those are the 3. I told you this on Friday, I believe, when Keenan was asking more questions. It's fine. I'm just going to bug you about it. So PBS, those are the 3 exceptions: phosphorus, bromine, and sulfur. And what this means is that the central atom can have more than 8 electrons. And so all of these will, what is that? All of these will break the octet rule, meaning they'll have more than 8 electrons around them. So some examples of that would be PCl3 and PCl5. Okay, so PCl3, PCl5. So phosphorus, like this, phosphorus technically has, I believe it's 5 valence electrons. So phosphorus, if you look at the periodic table, is right below nitrogen. So we would see it existing like this. I'm going to just start the other one right away. So 5 valence electrons surrounding it. So as far as PCl3 goes, there's 1 chloride, there's 2, there's 3. Chloride has a valence number of 7. Like this. And so pretty straightforward for PCl3. You just connect the dots and you're good to go. Now, in this case, as far as the octet rule is concerned, phosphorus has 8 surrounding electrons. So that's fine. This would be a normal molecule that we would see. And without knowing any of the exceptions, you should be able to draw this one. Where it gets interesting is when we get the 5 chlorines surrounding it, like this. So most of these, you can just very simply just connect the dots and draw bonds to them. Where you have the lone pair at the top, you're actually going to break that up and you're going to draw something like this. Now, in any other scenario, we'd say this won't work. If we check the formal charge, phosphorus has a valence number of 5, and now it has 5 bonds and 0 valence electrons, so that's equal to 0. We're fine. Where this problem would have existed previously is that this phosphorus right now has 10 surrounding electrons. In the past, we would have said, no, that's no good. Can't do that. Because we know that phosphorus is one of the exceptions, we can actually expand the valence shell and allow it to have more than 8 electrons surrounding it. So it has 10 surrounding it right now. And if you check all the chlorines, they're all the same. Chlorine has a valence number of 7, 6 dots, 1 bond. That's equal to 0. Questions or comments about that one? Cool. Next example that we can do is SF6. Just looking at this, I would guess sulfur's probably in the middle. Sulfur is also below oxygen, and so I know that it will have 6 valence electrons. Now, as I'm doing this, I would look at this and say, okay, I need to have 6 surrounding fluorides. Is sulfur one of the exceptions? And I would do my PBS or PBRS. And I would say, yeah, okay, sulfur is one of the exceptions. So I know that I can break those pairs of electrons up and have 6 different bonds coming off of that. So 1, 2, 3, 4, 5, 6, like this. I would know that each fluoride, this is a lot of dots to draw, has 7 valence electrons on it. And I would know that sulfur has normally this structure. So 6 surrounding electrons. There's also 6 opportunities with those fluorines for bonds to actually be formed. And so what you could do then is just instead do this 1, 2, 3, 4, 5, 6. So to confirm that the structure is correct, you would take sulfur, which has a valence number of 6, and say there's 6 bonds and 0 dots around it. So it does not have a charge. You'd look at fluorine and say, well, fluorine has a valence number of 7. There's 6 dots, one bond, so there's a 0 around it, and that would be true for all of them. And then the last thing you'd check is the octet rule, and we'd say that sulfur breaks the octet rule, and that's fine. That's okay that it does that. All right. Any questions about SF6? Cool. So here's the reasoning why we can do this. You'll notice that P, B, and S are all further down on the periodic table. They're not typically the elements we would work with, like carbon, nitrogen, oxygen, or fluorine. They're a little bit further down. I think they're the row down or 2 rows down. Um, the reason that we can do this and add additional electrons to the sulfurs, the phosphoruses, and the bromines is the idea that the S and the P orbitals are filled for the central atom. And then the d orbital, we had said that that's kind of the weird one, where when you were drawing Bohr diagrams, you could only go up to calcium and draw them correctly because those d orbitals are kind of weird, where they can be closer to the center at one point, they can be further away from the center at another point in time. And so it is believed that the energy difference between the p orbitals and the d orbitals isn't super large. And so the valence shell expansion, it seems like that's a possibility. I got a few questions, which was like some of the Google results that you look up will have a whole bunch of stuff, and then 3s2, 3p6, 3d4, for example. And what I told you in class was that that 3d orbital needs to come after the 4s orbital before you can do the 3d. The reason that some of your results on Google will have the 3D moved over into this location here, there is some kind of disagreement within the chemistry community about where that 3D needs to go. Some people say the 3D needs to be moved closer because of this statement right here. Because of this statement right here, where the difference between the p and d orbitals isn't super large. So that's why you'll see sometimes that one moved in front of the s orbital. I would rather, and the University of Saskatchewan, which is where I have my experience, would rather the D's come after the S's, simply to indicate that the valence electrons or the most outside electrons are believed to be here at this 3d4. So it's believed that those 3d4 electrons will be the first ones either taken away or added onto. In other words, those ones are the furthest away from the nucleus. So that's the reasoning for that. Um, there is a confusing calculation that you can use. I never think about that one. I instead just use this. So for those confused about the blue numbers where those are always coming about, formal charge is equal to valence electrons minus dots and dashes, or minus the number of electrons and number of bonds. And that's how you will determine what formal charge you have. This statement is important. Each atom in the compound will always want the lowest formal charge possible. So sometimes you'll need to make some adjustments to what you have drawn. Let's say that you draw something and you have a +1, a +3, and a -4 of whatever elements you have. You can probably readjust it so that adds 0, 0, and 0. You'll just have to move some electrons or some bonds around. Correct. Correct. As far as counting formal charge, you count them as 1. When you're counting the octet rule, you count them as 2. Yeah. So we're going to do POBR3. POBR3. As far as this one would go, um, it's probably going to be the oxygen or the phosphorus in the middle. In this case, I know that it will be the phosphorus. How can I explain that? I know. Here's how I know that it will be the phosphorus. If the oxygen's in the middle, oxygen looks like this. For there to be three BRs around this, I would have to break up one of these lone pairs of electrons. I don't really want to do that. And so what I'm going to try instead is I'm going to try putting the phosphorus in the middle first, and we'll see if that works. And so when I draw phosphorus, I end up looking like this. Now, seeing that, what I'm looking at there is I'm going, okay, well, what I can see right now is that there's a potential for an oxygen to be over here, a bromine to be here, a bromine to be here, and then I guess there would have to be a bromine on this side as well. So that's the only one. The top one right now is the only one that I'm like not super certain about how I'm going to handle that or how I'm going to move electrons around. So bromines all have 7 valence electrons, like such. And oxygen has 6 valence electrons. I'm going to draw it so that my single dots are closer to the phosphorus, like that. So 2 of these are really easy. I guess 3 of these are really easy. That's an easy connection between the phosphorus bromine. That's an easy connection between phosphorus bromine. These electrons here are both single electrons. So again, that's an easy connection. And now I'm left with this kind of awkward situation where I have a pair of electrons that I don't really want to break up on the phosphorus, and I have 2 singular electrons, one on the bromine, one on the oxygen. So I am going to break these up, and I'm going to try doing this. Lewis structures end up being, and I mean, even as you get further and further in your chem career, Lewis structures end up being a lot of guess and check. A lot of, I don't know if this is right, but let's check and see if the formal charges make sense. So first thing I'll check is the octet rule. My BRs look fine. I've got 6 dots and a bond, so 8 total electrons. My oxygen, I have 4 dots and 2 bonds. Again, that would equal 8 electrons, so that one's fine. And then my phosphorus, I don't really care if it makes or breaks the octet rule. We see we have 5 bonds or 10 surrounding electrons, so I mean, as far as we're concerned, that one's fine. The next thing I'd check here would be formal charge. Looking at my bromines here, valence number of 7, 6 dots, 1 bond. Okay, so that formal charge is equal to 0. And I know that all the bromines will be the same. We check oxygen here and see, okay, well, I have 4 dots, a valence number of 6, 4 dots, 2 bonds. It's equal to 0. And then I could check phosphorus, which has a valence number of 5. I see 5 bonds and 0 dots, so that's also equal to 0. Before I show you a hypothetical scenario that can happen, does anyone have any questions? Cool. So, one of the fun things with molecular geometry is that once you get this final solution here, you can kind of start to predict how this thing will react. Usually, something wants a charge somewhere if it's going to react. So, I'm going to just erase these formal charge numbers just so I have some additional space. Here's how I would look at this and predict this particular molecule to react. There is the potential, we have said constantly that this bond is worth 2 electrons. There is the potential that this bond leaves and instead just becomes a lone pair of electrons. And so, what that would look like then is instead of it having a double bond between phosphorus and oxygen, it would be a single bond with now more lone pairs. This is still technically the correct answer. This POBr3 still technically has a overall charge of 0, but now there's a -1 charge on the oxygen and a +1 charge on the phosphorus. What that means is that there's a bonus electron over here that some other molecule will want to come and try and either take away or react with. We can also see that this actually starts to have a little bit of polarity now, where the middle of this is going to be more positively charged and the outside of it will be more negatively charged. So that is just to show you that these hypothetical scenarios where electrons are moving around exist. Both of the answers that we had were correct. This one, as far as like a test scenario where I gave you POBr3 with no charge whatsoever, would be more correct because this is more stable than having a negatively charged oxygen and a positively charged phosphorus. This is the more stable version of that. Questions about anything today, either of the two PowerPoints?